All right, so hopefully you are happy with how you did on your test. Don't expect tests to be graded that quickly all the time. Ain't happening. But let's just do a little recap because we're moving on in our list here. How do I find the pH of strong acids and bases? Negative log of what? The OH or the acid or base concentration. Weak acids or bases, what do I do? Rice table and add it to water. Hydrolysis problems. Weak ion, add it to water in a rice table, and there's always something I have to do in every hydrolysis problem. Yep, flip Ka to Kb. Yep, I can tell why y'all's average is lower than last period's. Go Sheps. Today, we're looking at buffers. Today, I'm going to teach you, I'll show you both ways to actually find the pH of buffers, and we'll talk about what buffers are. But ultimately, the equation that you're probably going to end up using is called the Henderson-Hasselbalch equation. That was what I was going to name if I got another set of kittens, Henderson and Hasselbalch. Or Clausius and Clapeyron. I'm stuck between those two. I think Henderson would be a cute cat name. I don't know about Hasselbalch, though. That's kind of weird. All right, so what's different about this unit is in our previous unit, we were looking at pH systems where we truly only had one thing affecting or contributing to pH. From here on out, we're going to have multiple things in solution that are in equilibrium with each other. The first thing, and this you actually did in pre-AP, you didn't call it buffers, you called it the common ion effect. But basically, if you have a system at equilibrium, I'm going to use HA as my example of a weak acid. We would get this in equilibrium with each other, right? What a common ion effect is, rather than before, when we were solving for problems and you did rice tables, you pretty much were only given like the molarity of the weak acid, and this would be 0, 0, and then you'd solve your rice table, right? Well, in the common ion effect, what's going on is from the get-go, you have the presence of some sort of molarity of the conjugate to that weak acid. The fact that you have the conjugate acid, the weak acid and its conjugate base present at the beginning is what we call a buffer system. So the definition of a buffer is a solution composed of weak acid and its conjugate base or a weak base and its conjugate acid. It has to be weak because strong acids and bases don't have conjugates. And why do we care about buffers? Well, we care about them because buffer solutions basically refrain from changing pH very, very much. They protect different biological systems. We have buffers in our blood to keep us from getting acidosis and things like that. And the way it works, and that's what I'm going to show you now. So in our blood, we have, it's not exactly this, but I'm just starting from the step 1 to make it a little bit easier. What do we get here? H3O plus and HCO3 minus. Now it's not really, it's actually, this is Ka1. In our blood it's actually Ka2 to 3 that we have, but this is good enough to show you the example. So we have the carbonate ion in our blood helping us maintain pH levels. Because we have present both this and this at equilibrium, we could throw a bunch of acid in our body or base and would help maintain that pH level. So for instance, remember, in our system, if we have a little, this is our blood. That's blood. We have H2CO3 and HCO3 minus floating around. So if I was to come and like inject myself with a bunch of acid, not in a good way, I could buffer, I could protect the pH of the system by buffering it using the components of the buffer. Which one of these two components would react with H+? So H+ would be absorbed by the HCO3 minus, and this is not an equilibrium thing, okay? When we have an attack of an invader to a buffer, it is going to completion. And what are we going to make? H2CO3. Notice that we took a strong acid and converted it to what? a weak acid. You see how that has less of an acidic effect on our pH in our system? So not only did we create a weak acid, we created an acid that's already in our blood, right? So we're just going to shift the equilibrium a bit. But this protected and absorbed that H+, creating a weak acid from a super, super strong acid. So buffers can take hits from the acidic side. They can also take hits from the basic side. So if I were to somehow drink soap, what would it react with in our blood? Which one? H2CO3, and it would absorb it and turn it from a strong base into the weak base of HCO3-. So again, that doesn't affect our pH as much. Now the buffer is going to have its limits. The buffer will have a certain capacity. If I keep adding H pluses and H pluses and H pluses, I am going to run out of these. And so this will go straight to the pH and jack that pH up if I pass my buffer capacity. And then the same thing on the basic side. If I add too much base, I'm going to use up all of my weak acid. So that's what a buffer is. It's made up of a weak acid and its conjugate base, or a weak base and its conjugate acid, and its purpose is to resist changes in pH. Yes, Elsa? In our world, strong, when we say we're invading, it's going to be H pluses and OH minuses. Now, where those come from? HCl, H2SO4, HBr. Any strong acid contributes H pluses, which are strong, and that is considered to be a strong. And same thing with bases. Our OH minuses can come from any of the group 1 bases. Okay, so this page is the exact same explanation of what I just went through. So what I want to introduce you is to the Henderson-Hasselbalch equation. You are allowed to use rice tables, and I'm going to show you how to use a rice table, but I think knowing y'all and the laziness, and we'd like to get it done quick, I know that's how you guys are, I think you're going to prefer these equations. They look scary, but they're really not. There's two versions, a pH version and a POH version. They're on your AP sheet, so you don't have to memorize them. But pH is equal to the pKa. What's pKa? pKa. Negative log of the Ka plus the log of the ion over the acid. The conjugate is always on top of the acid. The conjugate is always on top of the base. When you're doing these, the thing that's charged, its concentration is always on top of the acid or the base. If you just remember ion over acid, ion over base, you'll be fine. Again, these are both, oh, don't die on me now, seriously? Now it's dying on me while I'm recording. This is fantastic. Okay, so I'm going to try to move on without freaking out too much here. So those little brackets, what do they mean again? Concentration. Since the brackets are concentration, you need to make sure that the concentration is used in moles per liter here, okay? In both of those spots. So let's go ahead and work a problem. Calculate the pH of a solution, which is 0.53 molar, some sort of acid. You see how that's an acid? What kind of acid is that? Weak acid. Now, here's the deal, and I'm really going to get on your period specifically about this. You guys are not classifying before you start your problems. I said that over and over again. You have to stop yourself and ask, hey, which category do I fall in? Some people were taking a hydrolysis problem and just treating it as a weak acid base. Doing crazy stuff like just adding the whole salt to water, not even taking the weak ion, like stuff that I didn't even know what was going on. It's because you're trying to rush through these problems and you're not classifying it before you start. Once it's classified, it's either number 1, 2, 3, 4, or 5 on this board. It's going to fall into one of these categories. Your job is to figure out which. So here we have a weak acid. Now, I know we have a salt here, but this is not a hydrolysis problem because you've got your weak acid, and what is included in that salt? The ion that, can you tell me about that ion? Chris, what? It's the conjugate base to this. Do you see how the ion of the weak acid only differs I'm sorry, the ion of the salt only differs the weak acid by 1H. Do you see that? Those are conjugates of each other. All right? So those are the two things that make this a buffer system. So we're going to use the pH version of Henderson-Hasselbalch because what we start out with is our acid. If we had a base and its conjugate acid, we would have used the pOH version. So again, Henderson-Hasselbalch, pH is equal to the pKa plus the log. You have got to be kidding me. It's frozen again. I flippin' am not happy right now. Plus the log, keep writing, of the conjugate. So the ion, in this case, over the concentration of the acid. So this Ka I looked up of this nicotinic acid is 1.7 times 10 to the negative fifth. So pH is equal to, what is P again? Negative log of 1.7 times 10 to the negative fifth plus the log of, what's the concentration of the ion? 0.50 divided by the concentration of the acid, 0.53. And I'm happy with that, 4.74. From here on out, on the test, I let you use your Ks. I wasn't too freaked out. I did freak out about sig figs if you went crazy and didn't do it right, but I either took 2 from the K or 3 from the concentration. I want you to follow the concentrations provided in the problem's sig figs, don't use the Ks for their sig figs. So here, that's 2 sig figs, just like the 0.50 and 0.53 are. Okay? All right. So that's pH. That's it. It's really easy to plug and chug and get your answer. Let's do this next one. This one I'm going to do 2 different ways. I'm going to do it Henderson-Hasselbalch and then show you how to do it with the rice table. So calculate the pH of a solution, that is that and that. I need you to classify. Don't just say buffer because we're on buffer day. What do we have here? A weak base. And this salt contains what? Which is the conjugate acid to that weak base. So that's why we have a buffer. Now notice we have a base and its conjugate acid. So what version of Henderson-Hasselbalch do I need? The base version. The Kb of NH3, by the way, is 1.8 times 10 to the negative fifth. You'll always be given that. So pOH is equal to the negative log of 1.8 times 10 to the negative fifth plus the log, which concentration goes on top? The ion, which is the same. What's the log of 1? 0. So in a case like this, where the concentrations of your conjugates are the same, the pOH is equal to the pKb. Does that look familiar? When did you just do this? In the lab. You just approached it a little bit differently. In the lab, I'm going to go off on a tangent here because I just think it's cool. In the lab, you were doing this, where these concentrations were the same. You see that? Isn't that the same as this? It's just a different version of it. And Henderson-Hasselbalch is just a logarithmic version of your K expression. All right? Okay, so what is my pOH? 4.74. So literally just plugging that in like that, super quick. Do you agree? Now I'm just going to show you, those of you who aren't interested in using a rice table, just you can put your pens down, but I do want to show you how you can also work these problems using a rice table. Once you recognize this is a buffer, you can use a rice table and do the following. You can say, okay, I'm going to take my weak base or my weak acid and add it to water. So in this case, it's our weak base. And you have to do it in that direction. It's the weak base or weak acid, the thing that's in the denominator here. Add it to water, and we get what? OH minus plus NH4 plus. The only difference in this problem to anything you've done is you now have 2 initial concentrations. You have this, and you have this. Now it's exactly a problem you already know how to solve. So you're going to go minus x plus x plus x. you're going to go 0.245 minus x plus x, 0.245 plus x. These cancel. What do I do next to find pH? Kb is equal to x times, I can drop my x, and I know my Kb, and then I can find this is equal to the OH concentration, so then I can take the negative log of that and be done, and that would give me POH. Oh, I just realized we messed something up. Okay, so this is actually, we forgot to subtract 4 point what? Okay, so we would do all of this and still get the exact same thing as we did when we were before. Here, we're not done because the problem's asking for pH. Okay? No, I don't care. Whichever you like better. I think at the end of the day, this is faster. But you can, if you prefer to do a rice table, it's fine by me. The problem with rice tables, and I'll just tell you now, people struggle with writing this equation. They struggle with identifying which is the weak acid and base and add it to water. They'll add like the conjugate to the water instead of the actual acid or base, so it throws them off. It seems like this causes a little less confusion, but I'm going to let you do either. I don't care. What do y'all like better? Henderson-Hasselbalch? Yeah. Okay. Calculate the pH of a solution prepared by mixing 20 mils of 0.3 molar acetic acid with 20 mils of 0.350 molar sodium acetate. This is worded a little bit differently. There's something different going on here. Can anyone recognize what's different in these? What? Well, what about the fact they give you volumes? They're not already in the same container. So when you mix them together, think back to the KC lab when we started those rice tables. What did we have to do to get the initial concentrations? You didn't take them off the bottles. We mixed them. We made 10 mil things. What did we do in the rice tables? Right, what was that called? We did dilution problems to figure out the initial concentration of both of those. In these previous problems, the solution's concentrations was already established, so it was already in one container. Here, we're mixing them. As we mix them together, they're diluting each other. Okay? So let's just really quick look at the acetic acid. The acetic acid, we originally have a 0.3 molar, 20 mils of it. What would be the new molarity when our total volume is what? What's our total volume after we mix? 40. So luckily it's in half, so it's 0.15 molar. All right, and then the sodium acetate, we originally had a 0.350 molar solution at 20 mils. What would our molarity be at 40 mils as well? Half of 0.350, 0.175. Thanks. That was a struggle. That's okay. I know you were there mentally, just the transition from here to here, not so strong. Okay, so now we have our original concentrations that after mixing happens. Do we agree that this is a buffer? Yes, we have acetic acid, which is our weak acid, and sodium acetate has the acetate ion, which is the conjugate base to the acetic acid. So what version of Henderson-Hasselbalch do you want to use? Lift your foot up. Huh? The acidic one, right? The Ka of acetic acid is 1.8 times 10 to the negative fifth, which is the same as the Kb of ammonia. So we get pH, Henderson-Hasselbalch acid version, minus log of 1.8 times 10 to the negative fifth, plus the log, what concentration goes on top? Ion, so it's 0.175 over 0.15. So pH is equal to 4.81. Got it? This is a little bit faster than doing the rice table. But again, if you want to, go for it. All right. Go back one slide. One thing I forgot to mention about this right here. Another thing that happens when you have the same concentration, what that means is this particular buffer could take pretty much the same number of hits from the acid side, acid invaders, as it can from the base invaders because they're the same. So the term used to describe this is an effective buffer. We say a buffer that has the same concentration of acid and conjugate base or base and conjugate acid is effective. And so we also then say, oh, in an effective buffer, POH is equal to pKb or pH is equal to pKa. So in effective buffers, pH is equal to pKa because the concentrations of those are the same. That's just a term you'll hear throughout. People say, what would an effective buffer have? Blah, 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 blah. They're talking about this being the same. Okay, so specify the reagents and the specific concentrations of each reagent needed to pair a buffer which would have a pH of 4.19. Okay, a pH of 4.19 is an acidic system or basic system? Acidic. It's smart for us to choose an acidic system. We could still get a pH of 4.19 if we used a basic system, as long as the conjugate acid was a super high concentration to that base, but the numbers will work out better if we choose an acidic system. So you guys pick a weak acid and a conjugate, a salt that contains that conjugate to that acid. Any of them. I don't care. What do you want to pick? H what? H2CO3. All right, and then HCO3 minus, but what salt would hold that? NaHCO3. So you guys want to do this. So I need someone, while I'm working the problem, to look up the Ka of H2CO3. It's in your notes from the last. It's at the last page of the last unit. It's going to be the polyprotic one, that small chart that has Ka 1, 2, and 3. Oh, I see it, Peter, right there. Let me take it. Carbonic is 4.3 E negative 7 is equal to the Ka. Good. Last time they chose cyanic acid, and it was a really small K, so it made the numbers kind of weird. But this is still going to be weird. That's okay. We're going to give it a whirl. So let me ask you, if I'm looking for a pH of 4.19, the hint is you're going to use Henderson-Hasselbalch. How can I use Henderson-Hasselbalch, though? Solve the ratio. I'm going to have two unknowns in the ratio, but we can figure that out in a minute. What I want to do right now is just say 4.19 pH is equal to pKa plus the log, and we're just going to treat this as a ratio. Let's solve for that x and see what we get. And we have a lab where you guys are going to be finding your own buffer concentrations to make. You're going to have to make your own buffer by solving for this on your own, so make sure you know how to solve for this. Yeah. All right, so that's equal to x. Now again, what is that the ratio of? The concentration in our system, which is the ion? The top one? No. HCO3. Oh, you meant the top one in the ratio. Yeah, thanks. I meant of these two, and I thought you meant this when you said top one. No, that. All right, and what goes on bottom? H2CO3. So we need to choose concentrations of these guys that are going to give us this ratio. So these numbers are definitely more doable than what they did last period. What concentrations would we use? One on the bottom. So we'd make a solution where we'd end up with 1 molar H2CO3 and 0.0067 molar. Now this is where you have to include, when we're talking about it, we're making it with this, because that's what the bottle's going to have on it that you're going to get from the stockroom. Molar sodium HCO3. Remember that sodium's a spectator. So if we have a flask, say we have a liter flask, it's an awesome flask, and we put 1 mole of that in and 0.0067 moles of that in, bam, we're going to have something that ends up with a pH of 4.19. So this is going to be one of your labs. I'm going to say, hey, Grant, make a buffer with a pH of 5.2. And you have to use these 2 things, and they're that molarity. Go. And you guys have to figure out how to do that and actually make it. And your grade is handing it to me and what my pH meter says. Does it match up with what you're supposed to make? It's very exciting. All right. Is everybody good with this one? No? Yes? Maybe? All right. Given a solution of ammonium chloride, what additional reagents are needed to prepare a buffer from ammonium chloride? So we have this. The question is, what else do we need to make a buffer? What is the weak base, Jamie? NH3, correct. If we have this, that's the conjugate acid to that weak base, so all we need to add to that is ammonia. All right? Letter A. Explain how this buffer solution resists changes in pH when A, moderate amount of strong acids are added. Well, when we add a strong acid, we're really adding H+. What part of this buffer here will the strong acid react with? NH3, and what is it going to make? NH4+. So we took a strong acid and converted it to a weak acid. So as long as we don't overtake that ammonia, we can take hits from the acid side and keep that pH the same, or close to the same. Moderate amounts of strong base are added. What would that react with? The NH4+, and we would make water and ammonia. So we took a strong base and converted it to a weak base. And that's going to help keep the pH down. Strong acid is hydrogen. Part C. A portion of the buffer solution is diluted with an equal volume of water. What happens to the pH? If we just took the buffer, and in our buffer, remember, we have NH4+ and NH3, and I threw in some H2O liquid, what happens to the pH? I heard it goes down. It's going down because we're diluting. No. I'm hearing y'all have a definite answer to this. And you're telling me increase or decrease. First off, it's wrong to think it goes either direction, because you can say, hey, I'm diluting the base and making it less basic. I'm making it less hydroxide-y. But you can also say, oh, remember, there's a conjugate in there as well, a conjugate acid. So you're making it less acidic-y too, right? What are you actually doing when you dilute both of those? Nothing. Why? The ratio stays the same. If I add 10 mils to this and 10 mils to that, yeah, I'm changing their individual concentrations, but I'm changing them the same. So adding water, the ratio of acid or base to conjugate stays the same. So the pH does not change. Same thing with doubling concentration. If I were to double the moles of each of those and double their concentration, because I'm doing the same thing to both, it would not change the pH. Peter's writing like a fiend. Okay, last problem. This is one of my favorites because we feel like we have power of hiring and firing people. Part A, this is just real quick. Specify the and this is a 1983 I wasn't even graduated yet here. This is from one of the first, I mean, AP, I don't know when AP chemistry started. I thought it was the late 70s. This is one of the first AP exams. Specify the properties of a buffer solution. Describe the components and composition of an effective buffer solution. So what's a buffer? Come on. A weak acid, not a weak acid and base, a weak acid and its conjugate base, or a weak base and its conjugate acid. What's the point of a buffer? It resists changes in pH. And then effective. What would be the most effective buffer? When pH is equal to the pKa, so therefore that means that the concentration of acid is equal to the concentration of the conjugate. Okay? Or base, conjugate base. All right, so now you're about to interview 4 people for a job at a lab, as a lab tech. And you tell them, all right, guys, I need you to tell me what you would use to make a solution that has a pH, a buffer solution that has a pH close to 9. So let's go through and look at each of them and see what they did. Archie A, says he would mix acetic acid and sodium acetate. Is that a buffer? Yeah, that's a buffer. So he made a buffer. I'm not mad at Archie. Then Beulah comes along. I feel bad for Beulah because her name's Beulah. Says she would mix ammonium chloride and HCl. What's wrong? You don't have a weak base. What's wrong? Well, yeah, they're both acids. It's kind of a problem, but there's one thing that is the first thing in the definition. Because this is a strong acid. That is a strong acid. You can't make a buffer with a strong acid. So Beulah messed up. Beulah needs to go look elsewhere. I'm not hiring her. I already know that. Carla C. says she would mix ammonium chloride and ammonia. Did she make a buffer? Yeah, she did. Good, Carla. Nice work. Dexter said he would mix ammonia and sodium hydroxide. Yeah, they're both bases, but freaking strong base. So Dexter, Dexter and Beulah, we'll see you next time. Thanks for coming. All right, like an American Idol, go get some experience and come back next year. So we have to decide now. I'm telling you, both of those we can get what we're looking for, but one of them is going to have ridiculous concentrations to get to the pH we want. What should we do? Who should we hire? Why are we going to hire Carla? She's starting with a basic solution from the get-go. Because what? Because she's a girl. Yes, exactly. Equal opportunity. Yep, that's right. But Archie might be a minority, right? So who are we going to hire, the minority or the girl, for equal opportunity? What if the girl is also a minority? Oh, well then, if the girl's a minority, then bang, she's hired. Oh, now Elsa said she's a disabled female minority. Oh, Lord have mercy. Okay, so we're going to hire Carla because she's choosing a basic system, which puts us in a better position mathematically to make molarities that are reasonable. We could theoretically still get a basic system from him. Remember, this is the ratio of AC minus to HAC. So if this is the conjugate base, if we just put a crap ton of AC minus in the system, we could force that number to become basic. It's just going to be a really, really high number of this or a really, really, really low number of that, which is hard in the lab to get good accuracy when we're measuring out so little amounts of stuff. So Carla is just the better option. So Carla, you're hired. All right, so that's it for today. Tomorrow it's bell-to-bell lecture. You're going to need calculators, you guys. You're going to need to drink your coffee or Red Bull or Monster or whatever it is. Be awake and ready to roll. Tomorrow's a big day. And then over homework, I'm giving you 2 problems on a video that you need to then watch as well, because we can't get it all done in one period. All right? That was nice. I couldn't tell if it was a hiccup or a hiccup cough or a... All right.